Okay, welcome everyone to our weekly seminar at the research division of the IAC. Today it's our pleasure to have Mireia Montes, most surely you all of you know. She basically graduated in Barcelona. She did her PhD here at the IAC. Then she moved onwards to several postdoc positions. In particular, she was in very prestigious places such as Yale, then Sydney, and then before coming back to the IC to the Space Telescope Institute in Baltimore. Now she has been with us how long? Like 4 years, 2 years. And then unfortunately she's moving onwards to continue and consolidate her career at the Instituto of Ciencias del Espacio in Barcelona. Today she's going to talk about unlocking the secrets of dark matter with low surface brightness observations.
Thank you, Jorge. Hi, everybody. Thank you very much for coming here to my talk. So I would like to start, saying that, no, okay. Now, one of the advantages of going, traveling to and doing postdocs in so many places was to learn about, different cultures and different people. One of the things that I like the most is this. This is the center of our Milky Way, as seen in Australia, and you can see here, like the basically the dust and the gas and the dust of our galaxy as we look into the center. So for the Aboriginal Australians, the slide would be good because it's loss of flash brightness. So here, the Aboriginal Australians look at not only the brighter parts, but also the darker parts. And for them, this was it was called the emu in the sky. As you can see, it looks sort of like an emu. And that's true. And, for them, like the position of the emu in the sky signal that different, like different epochs and different things. So that is to say that what we understand of our universe comes from the things that we see. So, for example, one survey that has revolutionized our understanding of the universe is the Sloan Digital Sky Survey. With Sloan, we could understand a little bit more of the evolution of galaxies, the formation of galaxies, things of our Milky Way, plenty of things. But as you can see here, this is an image from Sloan. Sloan is a little bit limited of the things that we could see. So, for example, if we look at the same thing in a deeper image with another telescope, we see more. We see, for example, that this thing over here is actually interacting with the bunch of galaxies here on the top, and we see the beautiful tidal tails of this jellyfish galaxy. So this is what we understand as the low surface brightness universe. This is the universe that it's largely unknown, not seen by surveys like big surveys like Sloan. So this low surface brightness universe encompasses, it's a very wide field and encompasses a large amount of things. For example, we can study the zodiacal light to understand the evolution of our solar system. We also can study galactic cirri, which are the filaments of dust of our galaxy that tells us about interstellar dust. And also we can study these low surface brightness structures around stars that tells us about mass loss processes and stellar evolution, etc. But where this field has shown, not very much shine, but where it has given the most, it has more importance, is in the extragalactic realm. And when we are talking about the extragalactic low surface brightness universe, we are talking about low surface brightness galaxies, so basically low mass galaxies, the stellar halos around, like more massive galaxies, and the intergroup and intercluster light, which is the diffuse light in clusters of galaxies. So for low surface brightness galaxies, we are interested in them because it's basically, well, first in Sloan, we are losing a lot of these galaxies. So 50% of the galaxies down to 10 to the 8 solar masses are not there. And if you go to 10 to the 7 solar masses, we are losing 85% of these galaxies. So, and this this mass range is where it is, it's where it becomes, it's important because it's where we start seeing the discrepancies between the number of galaxies that we predict and the number of galaxies that we are observing. And the thing is that we don't know if they are not there, which would mean that we don't understand our universe, or because we are not seeing them because, like there are. When we move to, like higher mass halos, when we are looking into, like more or less Milky Way like galaxies or above, we are talking about stellar halos. So all these diffuse structures that are around, these more high surface brightness galaxies. These stellar halos are interesting because it tells us about this evolution, the evolution of galaxies in the universe, and it tells us about also the find end of the luminosity function. So, more or less low mass galaxies will mean more or less stellar halos. And also it tells us about the dark matter halo of these structures. And if we go to higher and higher mass halos, we are talking about groups and clusters of galaxies. In there, we have what we call the intracluster light. So the intracluster light is this diffuse light that you see here, that it permeates the clusters of galaxies. So you have no empty space between galaxies in the cluster. And all of that is what we are understanding as the low surface brightness universe. So why we are interested in the low surface brightness universe when we want to know about the properties of dark matter? So dark matter, we don't know what it is. Still, we don't know what it is. We cannot observe the dark matter because it doesn't emit in anything so far. And when we are studying the low surface brightness universe, we are going into the lowest densities of stars. So, like we are seeing things that are faint, like these tidal tails that Julia saw, or the intercluster light. And these are those lowest densities of stars is where the dark matter dominates. So we are seeing stuff that can tell us about what is, let's say, below it, right? We are kind of tracing what is this dark matter. So I will show you like two cases that we are working on, one on the smallest scales and one on the largest scales. I'm going to start with this galaxy over here, that it's a galaxy that we call Nube. This is a work that that was published earlier this year with all these amazing people that helped me to do this work. So how we found Nube is it's a really interesting, by itself is a really interesting story, because as you know here, our group, the Loss of Us Brightness group, is interested in like optimizing deep observation so we can actually see the loss of us brightness universe and not erase it as normally the typical pipelines that reduce surveys they do. So one of the projects that was done like several years ago was the Stripe 82. So the Stripe 82, it's a stripe of Sloan that was observed several times. And because of that, like it reaches a little bit deeper than normal Sloan. So when in the process of like testing and like do some quality check in the images, one of my collaborators saw this kind of spot here that it doesn't seem like anything. But for example, to show you that in comparison, you cannot see anything in the normal Sloan. So that is something. So we went for it, and we decided to observe it with the GTC, because we have it there. It's the largest optical telescope, so we better use it. So with this camera, the Hypercam, we can get at the same time images in 5 different filters. So we went for it. We integrated for 1 hour, and we obtained the image of Nube. So we could, like basically say that, well, there's a galaxy there. It's not like a spot. So because we have the 5 different bands, we can get the spectral energy distribution of this galaxy. And with that, we can understand a little bit more about this object. We derive we fit models of single stellar populations, and we derive an age, rather old age, and a low metallicity. So basically, this is telling us that what we are seeing is like a typical kind of dwarf galaxy. Here, the disclaimer is that, as you see, Nube is quite transparent, and you see things that are, well, we don't know if they are in front of the galaxy or behind of the galaxy, or are in the galaxy. So in order to be, like conservative, just in case, what we did is to mask everything that we could see as a source there. So what you are seeing here are the properties of the diffuse light of the galaxy. If there are star formation spots there, we still don't know. But well, one of the problems that we have is that, yeah, we can see things, we can see very faint things, but we don't know where they are. Where it is closer, it is farther. But the cool thing with Nube is that Nube has some hydrogen. So we could get time with the Green Bank telescope to observe, to get a spectrum of that, and see a detection that places the galaxy at 107 megaparsecs. So more or less at the distance of Coma. The problem is, as you see, that the beam, so the resolution of the Green Band telescope is not great, which is this gray, this black to gray thing over here. And in that spot, there are a lot of other galaxies. So what we did is to look at any possible contamination that we can have that could create this measure that we are seeing. And the only thing was this galaxy over here that was at the same distance, well, at the same velocity that the detection, which is this galaxy over here. But as you see, this galaxy is located at one of the kind of like a very minimum of the beam response. So for this object to be responsible of the peak of the emission, it would have to be dampened by 10 to the 4. So it should be like it should have a lot of hydrogen that is not possible for a galaxy like this to have. So basically what and we look at anything that could possibly create this emission. We didn't find anything. So that's why we assume that this is emitted by Nube. So this is a little bit of the characteristics of Nube. Don't worry, I highlighted you the important ones. It's in a distance of 107 megaparsecs. It has the same amount of hydrogen than stellar mass, which, like, it gives us like a little bit of a clue that we are doing, things right. The effective radius, it's 7 kiloparsecs, which means that it's really extended. And also the ratio between dynamical mass and stellar mass is around 70, which tells us that, it's not like a lot of dark matter, but there's some dark matter there. So what makes Nube, like peculiar is that is very extended. So as you can see here, we derive the stellar mass density profile. And on the right, I compare it with other galaxies of the same mass. So in gray, you have normal dwarf galaxies. And you see that normal dwarf galaxies are really peaked, while Nube is really flat, really extended. And even if you go to these, like the most extreme galaxies, that the ones that are more extended, the ones that we call ultra diffuse galaxies, which is this one in green, it's nothing comparable to Nube. So that's the thing. So Nube is very extended, like it's 10 to the 8 solar masses dwarf galaxy, quite extended. So how can we create like a galaxy like Nube? So we went through several scenarios in order to trying to explain Nube. So one way of creating a galaxy like Nube is to have, if Nube is what we call it, a tidal dwarf galaxy. So when two galaxies with hydrogen interact, two high, like kind of Milky Way-like galaxies interact, because of this interaction, some of the hydrogen, like just goes into the, intergalactic space, and because of the disturbance, it starts creating stars. So you have like something that doesn't have dark matter, but it's sort of a galaxy, which is what we call these tidal dwarf galaxies. Because these tidal dwarf galaxies, they come from the gas from high mass galaxies. Normally, the metallicity that they have is the metallicity of this gas, which normally is around, solar metallicity. So as we can see here, the metallicity that we derive for Nube is quite low. It's kind of more like a dwarf galaxy rather than a tidal dwarf galaxy. And also, those galaxies, because they are not shielded by a dark matter halo, they are usually very short-lived. So normally, like the oldest one that has been observed, it's around 4 gigayears. And for Nube, we derive 9 gigayears. So it's old, and it's old, it's low in metallicity. So that doesn't seem like a tidal dwarf galaxy. Furthermore, when you see Nube, and you see also the galaxy that we assume that is the host of Nube, which is this one over here, you see that neither of those galaxies show any signs of disturbance. So it doesn't seem that anything happened there that could create like a tidal dwarf galaxy. And again, moreover, we have that Nube has some dark matter, while we expect those galaxies to not have any dark matter. So it doesn't seem that Nube is a tidal dwarf galaxy. Again, another way of creating, to puff the galaxies to create a galaxy that is so, extended, such as we see in Nube, is to have a tidal interaction. But as I said before, neither the host, neither Nube show any signs of disturbance. And, like in simulations, there has been shown that when we go to this low surface brightness, the low surface brightness that's similar to the images that we have of Nube, we will see those tidal tails even after, like long after the interaction. So it doesn't seem that Nube also comes from this scenario. And another scenario is that this puffing up of the galaxy, it was created by stellar feedback. So, or AGNs or supernovae that has released some energy into the dark matter halo, and the dark matter halo, because of that, it's too energetic for the microphone, has puffed the galaxy up. So for that, we went into two simulations, the Fire 2 simulation and the Nihao simulations. and we see what they are producing right now. So these are the two simulations, and we placed Nube where it will fall in these maps. So where you see the cloud is Nube, and you see that there's no way that you can create a galaxy like that in this simulation. So it doesn't seem that stellar feedback is capable of producing a galaxy like that. So problem is that now we are running out of scenarios within our, like our cosmological framework. So we said, why if it's not, like cold dark matter that is creating something like Nube? So we went and we looked at different, like dark matter flavors to see which one, like to try one. And we came across with fuzzy dark matter. So the cool thing about fuzzy dark matter is that, as you see here, this is Nube in blue. That fuzzy dark matter, like naturally, because of the properties that maybe Jorge will tell you, it creates this flat part at the inner parts. So this flat, what we call it, core, which in fuzzy dark matter is called the soliton. And after that, after this flat part, it follows like the normal Navarro-Franken-White halo shapes that we are used to. So, like we were encouraged by that, by like seeing like something like very similar to what we see in Nube. So we decided to fit this shape, this soliton shape, the shape that we see in the inner parts to Nube. This is a great warning here, that is that the light, that we are assuming that the light, that what we see traces the dark matter halo, which is something that the other Jorge will tell you, will explain you why. So basically, it's something on the lines of a galaxy like that cannot live in a Caspi, the normal Caspi cold dark matter halos. So we did that, and we with this fit, what we derive is a core radius, which is the radius of this structure. And with that and the mass of the halo, we derive the mass of the particle of this fuzzy dark matter, which is okay. You're like, oh, yeah, it's a number. But when you put it in context of other works that have studied fuzzy dark matter, you see that, well, we have with all these assumptions, we are getting something that is not too far, not too bad. So, for example, Andres Bañeres Hernandez, that is, I don't know if it's here, but maybe over there, doing like, things properly, like with the rotation curves of nearby dwarf galaxies, derived this mass for the fuzzy dark matter particle, which is, like not too bad. Also, full disclosure, there are some other works that derive like totally different masses for this fuzzy dark matter particle. But here we are not saying that it's fuzzy dark matter. What we are trying to do, or trying to say, is that there's a possibility to use these galaxies as a probe for the different types of dark matter. So this is the first summary, the first thing that I will show you. This is, basically what we've done for Nube is to use it as a kind of a probe for the nature of dark matter. Nube specifically is a very extended dwarf that cannot be explained, but what we know in the framework of the cold dark matter scenario. But maybe, like other types of dark matter can be the answer that we are looking for. And now, this is my favorite thing. I will bore you a little bit with the intracluster light. So the intracluster light is the diffuse light that that you see when you go deeper and deeper, you see some like diffuse light in clusters of galaxies that comes from the interaction between galaxies in the cluster. So in the interaction, there are some stars that are stripped off the hosts and end up, basically populating this intra-cluster medium. As you can see here, this is all you need to know about ICL creation. So this intracluster light is not a pure extension of the galaxies. It's an external, an extra component on top of your galaxies, which is extended, and it shows a velocity dispersion that is higher. So it's like a hot component. It's higher than the velocity dispersion of the stars that belong to the galaxy. And as you go from the inner parts of the most massive galaxy of the cluster to the outer parts, you see that the velocity dispersion raises until it reaches the velocity dispersion of the galaxies in the cluster. So it's a kinematic and it's a stellar, a kinematical different component. So one of the cool things of the intracluster light is that the slope of this component, of this stellar halo or intercluster component, this slope correlates with the mass of the system that we are talking about. And when we are going to higher and higher masses, this slope becomes very similar to the slope of the dark matter. So with that, that the simulations gave us, it's occurred to us, maybe we can use this distribution of stars, this distribution of intracluster light to see the distribution of dark matter. Maybe. So for that, what we use is the Hubble frontier fields. The Hubble frontier fields are 6 clusters of galaxies, the redshift range of 0.3 to 0.55. And these are the deepest images ever taken by the Hubble Space Telescope of clusters of galaxies. So are really, really deep. And not only that, not only the images are deep, but the Hubble Frontier Fields Initiative, they also provided the mass maps of these clusters, because those clusters were used as a gravitational lenses to see the high redshift universe. And in order to get the right properties of the high redshift galaxies, you need to correct by the effect of this lens, which is basically the cluster. So what we did here is, because we have the mass maps and we have the deep images, so we compared the distribution of intracluster light with the distribution of the mass of the cluster, and also we compare it with the distribution of, with the X-rays, what the X-rays were doing. And as you see here, only looking at it, the distribution of intracluster light and the distribution of mass are very similar. And however, the X-rays, in some cases it's more similar, and some cases it's just doing its own thing. And this is because these clusters are in the process of merging. So the X-rays they are from the gas, the hot gas on the galaxy clusters, and they behave like as a dissipative particle. So if you have like a collision over here, the gas will be colliding over here and emitting a lot in the collision point. While the intercluster light and the mostly dark matter will be doing their, they are kind of collisionless. They are doing their own thing. So because we're astronomers and we are not happy ever, just a visual inspection, a visual comparison is not enough. We need to, we want to quantify things. So what we did in this case is to use this metric that is called the modified Hausdorff distance. what the modified Hausdorff distance gives you, it's basically the similarity between two shapes. In this case, would be the intracluster light and the mass maps. And so basically what we did is compare like the different shapes at different radius from 50 to 140 kiloparsecs. And in red, you see the comparison between the intracluster light shape with the different mass maps. There are around 5 to 10 mass maps for each of the clusters, depending on the different groups and the different techniques that were used for to get the true mass distribution of the cluster. And because of that, because we really don't know the true distribution of mass, what we did is compare the mass maps together. So we have kind of the error on our true shape here, which will be these blue rectangles over here. And as you see, the comparison is really good. So it seems that using the intracluster light to trace the mass, the distribution of mass of these clusters it's a good thing. And why is that? Because like you might think this is weird. Why is this happening? So we know that the higher, like as you go to more and more massive satellites, you have more and more satellites, and these satellites tended to deposit the stars at larger radius. So basically, where you have it is an extended light profile. You have the stars living where the dark matter lives. And also, as I pointed you before, these stars, they are not bound to any particular galaxy. They are following the potential of the cluster. So basically, they are following, which is mostly dark matter. They are following the dark matter. So this combination of two things makes the intracluster light a really good tracer of the dark matter in clusters of galaxies. So, sorry, you might ask yourself why I put that. It's because what I was wanting to say is that opens the possibility to see, how the mass distributes in galaxy clusters, basically by obtaining a very deep image, instead of doing all these complicated steps of having, like this mass modeling of clusters. And why is that interesting? Why is looking at the distribution of mass in how the mass distributes in clusters of galaxies interesting? Because how it distributes tells us about, of course, dark matter. So here on the left, you see different simulations for different types of dark matter. As you can see, how much structure you have depends on the flavor of the dark matter particle. So basically, by having a tracer that is relatively easier than before, and having the access to lots of galaxy clusters and lots of distribution, maybe we can say something about dark matter. And like for a bonus thing, I will talk about these clusters, so MAC 0723, which are the first images of JWST. So the first thing that I have to say is that, like I've talked about this loss of brightness universe, but if you have ever talked about to any of us, you will know that we have like really nice images and really cool results, but it comes with a price. And the price is that, like normally the images that we have are not prepared for what we are doing. So images, like this probably is one of the best case scenarios in which we want to study this thing that is diffuse, that is extended, and we have like clearly here a strong gradient in the image that will basically bias our results. So we cannot do anything with, images like that. So what we normally are doing, if we are, like you talk to Julia, to Samane, to any of us, most of the time we are dealing with these things over here. So in this case, the image was like that. Again, this is the first image of JWST that was ever seen by the mortals. And this is our, so we reprocess the data and we end up with something like that, which is, like much better and something that we can use to study the intercluster. So once we have like the images clean, nice for us, what we see is this cluster has a lot of substructure. So it's elongated into this like right-left direction, so east-west. And you see that there are like some streams over here, and there's this like nice loop over there. So before going into like more details of why this is cool and this is important, I will tell you that what we did, our study of the intercluster light of this cluster, show us that this, what I told you before, this this slope of this halo of the slope of the intercluster light is very similar to what we are expecting for the dark matter. And in here, what I want to tell you is that already this property of the intercluster light tracing the dark matter has been used to improve the mass maps in these mass maps of the cluster. So for example, this in this article in Mahler et al. 2023, because there was this loop over here that we saw, they added an extra component that was not obvious in the velocities of the galaxies or anything. But they added this component over here into the mass modeling. And actually the RMS, so it tells you like how good you are retrieving, the mass maps, drop from 126 to 0.32. So it was a great improvement only by adding this component that nothing was telling you that it was there, but the intercluster. So I think that this is like very promising, and this is a way forward to understand a little bit clusters of galaxies and dark matter. So this is the summary of the second part. Intercluster light is a very powerful tool for, like to know about, like the evolution of clusters of galaxies, and understanding a little bit about our universe. And also it's a really powerful tool to trace the dark matter in clusters of galaxies. It might help us to understand the nature of dark matter, and also that is something that I haven't told you, but if you want, I can tell you a little bit more later about the edges of these clusters. That also relates about to the nature of dark matter. So this is the two things that I wanted to tell you, and thank you very much.
Hello. Thank you, Mireia, for the very nice talk. Questions or comments?
Mireia have very nice questions. I wish we had the coffee before the talk rather than after, because this is too early for me, I guess. So very nice.
It's not that boring.
No, it's not. It was boring. I was trying to keep up, but I need something. Anyway, never mind. So the thing is, I'm new at this field, and I have probably stupid questions. First, related to the second topic you were talking about. To what extent is intercluster light different from galaxies? I have this image of this ballet cluster where you have the gas going on one side with a shock wave, and then you have that the lensing map provides a mass map that is very close to the actual galaxy distribution. And from that map, I understood that more or less galaxies can be seen as frictionless particles that trace matter, right? Yes. Here you're talking about intercluster light. So what are the differences between the galaxy distribution within a cluster and the intercluster light?
So
is there significant differences between the two components?
No, Not really. So the intercluster light is what happens when, you know, like when you have this interaction between the galaxies and the cluster. So so basically what happens is that these stars, instead of like belonging to a galaxy, they end up, you know, like just populating this intercluster light space. So in that sense, when we are talking about the bullet cluster, one of the the good things about having intercluster light instead of having the galaxies is that you intercluster light is always sorry it's always it always belongs to the cluster. So it's not like for example, when you're looking at the bullet cluster, you really need a spectroscopy to see which galaxies are belonging to the cluster.
Okay.
But with the intercluster light, you don't have this problem.
It's
It
there.
just is there. It belongs to the cluster.
Okay.
So in that sense, you will you have the intercluster light sort of what you said about the galaxies. So it's like a collisionless component. But in this case, instead of having like, you know, like more discrete ones, you have like a continuum one.
Continuous mapping.
Yeah.
And this connects to my question related to the left figure, to the nube, right?
Nube, yes.
And this is, I understand again what you you had 5 bands, you made a fit of for spectral energy distribution. I guess you're ignoring all the knots.
Yes, what I was saying, that's with when we are deriving the H and the metallicity, it's only of the diffuse light, because we don't know if those clamps belong to the galaxy or not. Right. So instead, you know, to be like, you know, like the most conservative in this case, I mask everything.
Okay. And then you said that you found some H1 emission, and that could not belong to a background galaxy because it would be way too bright or something.
So when you look at the if I can, maybe too many slides. So when you see the map of you know, like the galaxies over there, so what we are trying to see if this could be created by something else, because the resolution that we have from the Green Bank telescope data is not great. We are working on it. We have VLA images. So we need to make sure that what we are seeing belongs to the thing that we want it to be, and not from anything else. So what I did is, you know, go through and go through you know, spectroscopic, photometric redshifts, even, you know, by eye, to look anything that could create this emission. And the only thing that was closer was this galaxy over here. But because it's so far from where we have the peak of the emission, so it should be dampened by, I don't know, like less than 0.05%. So in order for this galaxy to have to create that emission that we see, should have a huge amount of hydrogen that is not realistic.
My very last question.
Yes.
What is the prospect? So it seems that you're using ICL, you're using this very deep imaging to constrain dark matter somehow. So is there an ongoing program? I've been hearing this for a few years now, so I guess that you may have a significant amount of deep images and a catalog of galaxies, or maybe not so many.
Not so many.
So are there prospects to actually, I mean, is there a plan like, okay, as you know, as we collect 1,000, 50,000 of this type of galaxies?
50,000. I wish we.
So
it's more like always like where the ballpark numbers are, like we are now reaching to hundreds of it.
How many of them would you need to actually constrain fuzzy dark matter? Because you know, discard.
No. What we need is to for the fuzzy dark matter, I think that what and we are trying is basically to go to you know, like the most range of masses as we can have. But problem with this is that, you know, distances, if we want to so basically what we have to rely is on the light that we see, because getting a spectroscopy is really hard. So yeah,
I see what you're saying.
It's numbers.
Thank you.
Thank you for the very nice talk. Have a couple of questions. One is about groups of galaxies. Is like in a group like in Milky Way, would you expect to be inter-group light? And has this been seen in any group of galaxies?
Yes, the group of galaxies is a little bit more complicated because we have a huge range of observations. We have from the ones that have like no intracluster light that has been observed to the ones that have a kind of a lot, like 20-30% of the light of the group. It's in the intracluster lights component. We don't know exactly why, what is the dependence, because we really don't have that many observations. It might be there's some indications that well, there's the dynamical state, which seems to correlate with the amount of intercluster light. How compact is the group of galaxies? Seems that more compact groups have more intercluster light. And but there's no correlation between the fraction of intracluster light and the mass of the halo. So between groups to very massive clusters, it seems to be more or less the same amount of light in this component.
Thank you. And then about the knots in Nube, have you tried to do some like statistical thing to see if there are more knots inside Nube than outside?
No.
Okay.
No, but it's a yeah, might be like a good idea to see if there are here more knots than.
Yeah, and then the other question would be, would they be bright enough to do spectroscopy on them and see if they how they move?
Well, we are trying.
What is the brightness of these things?
So the central brightness
is not the surface brightness, the knots.
Of the knots.
The magnitude of the knots.
Oh, I don't remember. The surface brightness. Where I'm going in the opposite direction.
Because when you do the surface brightness, I guess you remove the knots as well, right?
Yes, of course. Yeah. Everything that I derive for Nube, it's just masking everything. So the central surface brightness of Nube is 26 point.
Yeah, but the point is the magnitude of the knots.
Yeah.
Because if they are bright enough, you could actually do spectroscopy on them and see if they move like the galaxy, if they have the same velocity as the H1.
Yeah.
And then because it would be very nice if some of them could be actually clusters. Clusters.
Maybe.
Would be an extra constraint to the dark matter that you have there or the matter.
Might be a little bit difficult because of the crowding.
Well, this is 1 arcsecond?
This is 10.
10 arcseconds. Okay.
So yeah.
Okay.
So about Nubes, I was wondering, have you considered the fact that he's not necessarily in equilibrium? Because in the Milky Way, we are seeing some galaxies that we thought are in equilibrium, but we see several components inside. And I was wondering, because I guess you have some scatter, right? So you can get in the metallicity and so on, but also in the velocity. So I was wondering if it's possible.
So the Nube the stellar populations are very well mixed. Is what I can say about Nube. About, like other like dynamical things going on in Nube, it's a little bit more difficult because.
Okay. Because then in the case that could be possible with a cold dark matter scenario. If you have this accretion and resonance accretion that makes that.
I mean, it's quite isolated. So the distance to the nearest one is 400 kiloparsecs. So it seems to be quite isolated.
Yeah. And the second thing was you were saying also that the shape of the ICL can tell you about the type of dark matter.
The distribution of dark matter, and the distribution of dark matter comes. It comes from the type of particle that you have. Yeah, it's what I show in the. Oh my god. this. So how it distributes inside of clusters of galaxies depends on what type of dark matter you have here. So there are some that you have less structure, some that you have more structure.
Mireia, thanks for the nice talk. Following up on what Guillaume was saying, and about Nube, the hypothesis of tidal disturbance, I think that there have been in-body simulations showing them if the time that's passed from the last pericentric passage is larger than a few dozens crossing times meaning within of a star within the galaxy itself, you would not expect to see tidal tails anymore. So what you're saying, if the closest galaxy is at 400 kiloparsec, then definitely you would not expect to see tidal tails in Nube, even if it has been tidally affected by a passage to the large host. And also the same, some other simulations that have been run from the local group, because we do have, for example, some of galaxies which are found in isolation, no? And they have demonstrated that through three-body interactions, you can actually shoot away a dwarf galaxy at 700, 800 kiloparsec from the large host, whilst before these were actually found much closer. So maybe, you know, some actual simulations to completely exclude the hypothesis of tidal disturbance might be useful in the case of Nube.
Yes, we looked at the time scales of looking at seeing the distortions, and I don't know if Nacho you remember the number, but we were calculating that in the center, yeah, it would be like a short time. It will become, you know, like more like normal and symmetric, but in the outer parts, it will be like longer. Of course, we cannot rule out that, you know, like if it was born and then it was ejected, it might be. But so far, what we can see and what we can measure is this.
Yes, so the orientation in which you are seeing it.
Yeah. By Jorge. So in Jorge's simulation, it was, I don't remember the time, but it was quite long. Yeah. This, sorry. Yeah, this one. Yes.
I mean, I'm surprised because it's not what we see in other simulations.
If you go, the point is that if you go really, really deep, you can always see the tail. Just a matter of
Okay, maybe we can talk about it. Sure. But at some point, the bound stars.
But if you are really far away, like isolated, it could be my point is always a matter of doing. So you have enough knowledge.
We agree to disagree. Anyway, just a very naive question. Say, if you would reobserve Nube with something like HST, I don't know if it has been done.
I've tried. Say it.
But let's say, or better, okay, so since we have not tried with Nube, have there been a test comparing the sizes of these ultra diffuse objects that you get with the ground-based telescopes and HST?
Yes, they are similar.
They're very similar. Okay, so there is no overestimate of the sizes.
I mean, it depends on, for example, if we look at, Julia's galaxy, I'm going to call it Julia's galaxy. That depends on, like, of course, it depends how deep you go. And This one over here. Of course, it depends on how deep you go and if you have tidal tails or not. But normally, like let's say like normal, like normal observations that you don't see, like things like that, it's comparable. When you go to, higher resolution like Hubble and ground-based imaging.
Okay, I propose that we continue the discussion over the scientific coffee. So let us thank Mireia again for her beautiful talk.